Good afternoon, everyone. I'm going to present some recent attempts, somewhat primitive attempts at this stage, to test MOND in redshift galaxies using rotation curves. So why testing MOND at high redshifts? Well, first of all, in MOND, the dynamical laws of galaxies, like the RAR, the ETFR, and so on, are supposed to be fundamental laws of nature, so they should exist at any redshift. Whereas in lambda CDM, they emerge from the complex process of galaxy formation, and so at some point they must break down. So potentially this is a way to differentiate between MOND and lambda CDM. So I know that many people in this room don't need convincing about which one of the two is right. So let's just go straight to why it's interesting just for MOND. And one of the reasons is the MOND cosmology connection. So we heard several times during this conference that A0 is numerically close to C times H0. So one may say, okay, maybe then A0 evolved with Z like C times the Hubble parameter, or some other function of the redshift. But A0 is also numerically very close to C squared times the square root of the cosmological constant. So if the second equality is more fundamental, we may expect that A0 does not vary with cosmic time. So if we can trace the evolution of A0, we may actually inform fundamental theories about which one of these two connections is more important. And finally, we heard yesterday from Ricardo that the distance redshift relation may be an issue. In lambda CDM, in fact, we find that IZ galaxies are extremely compact, and so we can wonder, in MOND, should we use the same angular diameter distance relation as in lambda CDM, or maybe we need a different one, and we can inform theories with observations. So in this talk, I will not address all these points. We are not there yet, but I will show you some really first steps in this direction. Now, if we want to do this exercise, we need to trace rotation curves across cosmic time. So we need proper tracers for the gravitational potential. At redshift 0, we are spoiled because we have access to many different gas phases. We can trace ionized gas using H-alpha molecules using CO transitions, and atomic gas using H1. And H1 in particular is extremely important because it is very extended. So this is on the left an optical image of a beautiful galaxy, and you see 6946, where you can appreciate the extent of the star-forming disk. So essentially stars, H-alpha emission, and CO. But when we look at the H1 disk, it's much more extended. This is the same scale, and it's a general feature. Typically, H1 disks are a factor of 2 or 3 more extended than stellar disks. And therefore, we can trace the kinematics all the way out, where the accelerations are small, and the MOND effect is large, and so we have a very powerful test. And this has been done for many years. This is a plot from the PhD thesis of Peng-Fei Li about, fitting with MOND very extended H1 rotation curves, but really the pioneering work here was done mostly by Bob Sanders and several generations of students at the University of Groningen during the 90s, where for the first time, it was shown that MOND can indeed fit H1 rotation curves very well. In the future, we will have the square kilometer array. This is actually an image of Meerkat, which is an existing telescope in South Africa, already operating and providing beautiful data. And Meerkat will be expanded and will eventually become the SK MID by 2030s. And so we will have a new wonderful machine to get very deep H1 observations and also push back in redshift. But actually, one of the goals of the SKA is to detect an H1 mass of 10 to the 10 solar masses at redshift 1, possibly spatially resolved. It's not clear yet whether we can reach that goal. So we understand that if we want to go to really high redshift, H1 is not an option for our generation of astronomers. And so we have to look for different lines. What is available? In the redshift window between 1 and let's say 4, a lot of work has been done already with the H-alpha and oxygen 3 lines, so ionized gas, which can be observed with near-infrared spectroscopy. And more recently, we started to use high-transition CO lines using the ALMA telescope. And then at redshift even higher than this, above 4, JWST will be able to provide H-alpha and oxygen 3, but actually I think that the most promising line is the ionized carbon line, the C2 line in the far infrared, which I will discuss later during the talk. So let me start with the redshift window between 1 and 3.5, that is typically called the cosmic noon. And in this talk, given the limited time, I will just focus on CO lines from ALMA, because cold gas, in my opinion, is actually a more robust tracer than ionized gas, especially at IZ. So this is a plot of the frequency bands covered by ALMA versus redshift, and the different line shows the observability of different emission lines. So in this talk I will focus on these galaxies that we observed using ALMA. The first one is redshift 1.5, for which we get the CO2 to 1 line and the CO3 to 2 line. And then a second one at redshift 2.2, for which we get the CO3 to 2 and the CO4 to 3. So these are the two galaxies. They are close on the sky, although they are not physically associated. And this is very good because with a single ALMA observations we can get them at the same time. So we can optimize the exposure times. So the gray is an HST observation, and the contours indicate the emission line maps from CO. So essentially we got two birds with one stone, but no animals were harmed in this world. So this is actually the first galaxy in more detail. This is CO2 to 1 and CO3 to 2. These are the intensity maps. These are the velocity fields. So clearly these are rotating disks. And on the right you see so-called position velocity diagram. I don't want to enter into much technical details, but just let me tell you what these are. So this is the distance along the major axis of the galaxy, and this is the velocity along the line of sight. And these contours represent essentially emission at different signal-to-noise levels. So in this case we have 2 sigma, 4 sigma, and so on. And if you read a paper deriving the rotation curve and doesn't show this diagram, you have to be very skeptical, because this is what tells you whether a rotation curve is correct or not. And if you have experience with that, for example, you can see by eye that this rotation curve is flat. This is the approaching density inside, there is no doubt about that. And of course we don't do things by eye anymore, although it's a useful exercise to do. We now can fit a rotating disk model which is convoluted at the same angular and spectral resolution of the data, and then compare it with observations. So these red contours indicate the best fit model. And what we find in this case is that the average rotation velocity is pretty high, 10 at 40. And surprisingly, the velocity dispersion of the CO is very small. Actually, we cannot measure it. And this is just an upper limit that is driven by the spectral resolution of the ALMA instrument, which is extremely good. So the V over sigma ratio is very high, and this is just to say that these are pressure-supported gas disks, and we don't have to worry about pressure corrections or things like that. The rotation velocity that we see is a good, faithful tracer of the potential. And the same occurs for the second galaxy at redshift 2.2. This is again PV diagrams with our best fit model. And again, the V over sigma ratio is high. So next, what we can do is to take the HST images and derive surface brightness profile using standard techniques. And then we can use these profiles to actually infer the gravitational field of the stars. The V star that goes into a rotation curve decomposition. And so we can go and build a mass model. So this is a mass model in Newton without dark matter. And the three parameters in these models are the masses of the bulge, the gas, and the disk. And what we get with this model are masses that are actually quite realistic, in agreement with standard stellar population models and ISM models. Keep in mind that from CO2 to 1 or 3 to 2 is not trivial to go to a gas mass. It's not as trivial as for H1, where we have atomic physics. This is astrophysics. And so there are assumptions in this, but the numbers that we get are realistic. So these already tell us that we are not reaching the MOND regime. But actually, if we make a MOND fit keeping keeping A0 at the same value that we observe at redshift 0, you can appreciate that there is a mild MOND effect. Let me go back and forth. So you see the bulge stays almost the same, because to explain this point we need the bulge in the Newtonian regime. But then the gas and disk masses decrease a little bit, less than 50%, so we cannot really distinguish between the two scenarios, but it's an indication that we are getting close to the interesting regime. And then we can play other games. We can say, okay, what if A0 varies with 1 plus z to the power of 3.5? That would be an interesting time evolution. And the effect is that the gas disk and the stellar disk go down in mass, because we are essentially boosting the MOND effect, right? And in this case, we get masses that are of the order of 10 to the 10 that are not ruled out, but they start to become suspicious, right? We really have to push the models in that direction to get these low masses. And then if we assume an evolution which is stronger with redshift, the gas and disk masses are pushed down. Also the bulge mass is pushed down, because the galaxy would be now fully almost in the MOND regime. So I think this type of evolution is really ruled out. So a strong evolution with redshift is not acceptable. Now let me move actually to higher redshift, so we can actually test this type of things even better. And in particular, I will focus on the window 4 to 5, in which we can observe the C2 line at 158 micron of singly ionized carbon. So this line is very interesting because it's one of the main coolants of the ISM, so it's very strong, and it in fact has been detected up to redshift 9 with ALMA. And it traces cold gas that is cooling right now. It's the coolant. And the ionization potential of the line is 11.3 electron volts, which is very similar to the one of the H1. So we expect that this line is actually a multiphase gas tracer that may trace a combination of atomic gas, like H1, molecular, and ionized gas. So there is the potential for this line to be possibly as extended as H1 disks at redshift 0. So a few years ago, I started a project called TRICEPS, that stands for Tracing Rotation with Ionized Carbon in Nearly Permeable Systems. So the idea was relatively simple. We took a sample of 15 galaxies in this redshift window that had known C2 fluxes from previous observations larger than 2 JWST, and we did follow-up observations at very high resolution, between 0.05 and 0.2 arc seconds. That corresponds to 0.5 to 1 kpc using the usual angular diameter distance relation. And these objects were originally identified in different ways, but essentially we are probing high mass and high star formation rate galaxies in this window. So of course we had to start somewhere, and we start from the monsters that are easier to study. So the data analysis is in progress, so what I'm going to show now will probably change in the future, but I think that the main message is already very clear. And the first message is that there is rotation ubiquitous everywhere in all the systems that we observe. And in particular, there were indications for this from previous observations, but now with the type of angular resolution that we have, that allow us to resolve the kinematics spatially with high confidence, there is no doubt that these are regularly rotating disks all the way up to redshift 5. So let me actually focus on the object up here. That this one has already been published a couple of years ago in Science. It was our pilot observation to set up all the observational strategy. And you can appreciate that the velocity field is extremely regular, so we can really trace an accurate rotation curve and therefore infer the total MOND potential. This is the C+ map, which gives us the gas distribution, and so we can infer the contribution to the rotation curve driven by the gas, at least the shape. And the problem here are the stars, because for these objects, at the moment, we don't have very good images. So we did a sort of hand-waving approach. What we have is the sub-millimeter continuum, which is this image there, that is tracing hot dust heated by young stars. So we can assume that the star-forming disk has a similar distribution as the dust emission. And then we also include a bulge component by hand. So we have an additional passive component in the center, spheroidal light, and this would be the star-forming disk component. So the mass model that I'm going to show in the next slide should be taken with a grain of salt, because we don't really trace the stellar mass distribution as we do at redshift 0, but this is the first thing we can do. So these are now MOND fits at redshift 4 to 5, keeping A naught fixed. And what you can see is that essentially you can fit the rotation curves very well. We get baryonic masses between 10 to the 10 and 10 to the 11 solar masses, which is what we expected from the luminosities of these objects. In most cases, we really need the central bulge. So it seems that bulges are in place already at redshift 5, and this is somehow consistent with the JWST results on passive galaxies type Z and early galaxy formation and so on. The other thing you can notice is that the outer radii are small, a few kpc, and so most of these fits actually are very close to Newton. We are not at the A naught level yet. Another way to look at this is actually to compare the high redshift data with the local data. So on the left, I'm plotting on a log-log scale the rotation curves from the Spark database in the, let's say, blue color scale. And I'm also adding in yellow some new rotation curves from Di Teodoro and collaborators that are for extremely massive spiral galaxies that are rare. We don't have many of them in Spark because our sample is somehow limited in a volume of 100 megaparsec. But if you go to larger distances, I mean, there are spiral galaxies rotating at 500, 400 kilometers per second. I do that because when we put the redshift data, many of them are rotating at those speeds, right? Some of them are more consistent with, let's say, normal spiral galaxies with rotation velocity between 2 and 300, but some of them go up to 400 kilometers per second. So possibly we are picking up, you know, the most massive, the progenitors of the most massive disks at redshift 0. And then what you can appreciate on the right panel is the radial acceleration relation. So the blue are the local data, and the red and other symbols are the galaxies that I've discussed so far. So you see that essentially we are close to the 10 to the minus 10 acceleration, but not there yet, right? And we would really like to get there. So is there hope? I think there is hope. So this is an experiment from Michele Ginolfi, which has been stacking different C2 maps all together in order to increase the signal to noise ratio in the other parts. And when you do this stacking exercise, you see that actually the size of the C2 emission increases and reaches diameters of the order of 15 kiloparsec or so. So a factor of 3 larger than the data that we have. And for example, this is the normalized C2 surface brightness profile. I think it's quite solid up to here. So the C2 on average may reach radii of 10 kpc, again assuming the usual angular diameter distance relation, and possibly there is also this tail up to 15 or 20 kpc. So if we push hard and we beat down the noise in the data, we may be able to get more extended rotation curve. So this is something I'm trying to do. I've asked observations for a couple of galaxies to go very deep. The proposal is currently under review, so I don't know the outcome. I hope I will get the data. We'll see. But the other thing that we can do is actually to get JWST images, and likely the proposal was approved. And so with JWST, we will now have the real actual stellar mass distribution. So we could actually build mass models with a similar accuracy that we have at redshift 0. So to conclude, at cosmic noon, so let's say between redshift 1 and 3, unfortunately the H1 line will be largely out of reach, even with the SKA. And the CO and the H alpha rotation curves do not probe the MOND regime, even if we push quite intensively with integration times. So from my perspective, this redshift window is not very promising for testing MOND, but paradoxically the higher redshift is more promising because the C2 line can potentially be very extended down to the MOND regime, and we can also use this synergy between ALMA and JWST to build accurate mass models in the future. And finally, about the evolution of A0 with redshift, what we can say at the moment is that a very strong evolution is ruled out, not by the rotation curve fit itself, but because we get baryonic masses that are uncomfortably low, whereas a more mild evolution, I would say, is still on the table, but it smells funny, because, again, the masses are a bit low, but to really test this, we have to improve our understanding of gas masses in this redshift window. Thank you.
So I'm going to go for the process.
Yes, thank you. It was very interesting. Yeah. In fact, you said that at higher redshift we will have more data because of C+, but in general, C++ might not be in equilibrium, because if it was in equilibrium, you have a gradient of metallicity that prevents you to look at higher radius, but here you might have some outflow. Then maybe the galaxies are not very regular at this redshift and these scales. That's the problem.
So, as far as we can tell for now, I mean, this is one of the most symmetric rotating disks that I've seen, including galaxy generation 0. So I think the equilibrium issue, at least in the inner part, is not a problem. When we will get data deeper in the other region, we will see whether maybe there is some gas accretion going on or some outflows going on. But as far as we can tell from the data that we got, you know, look at this one, for example. This was a very beautiful case. Extremely regular.
As you say, you are not in the MOND regime. To go further away, it would be difficult.
Yes, I mean, we have to get the data, we have to look at them, and then...
So my more important comment has to do with the logo of your tricep thing. I think you're showing the bicep, not the tricep. Wait. Yeah. No, look at the coloring. It was done on purpose. Yes, okay. The less serious comment is that you actually are testing MOND in a way, because the fact that for high accelerations you don't expect any disturbance is also a prediction of MOND. I don't see that it follows from that from lambda CDM unless you put it in by hand. Because why should you have no dark matter with accelerations larger than A0? Yeah. So, and the other thing is the testing of the Z dependence of A0 could also be done even if you don't reach the MOND regime per se, because if, for example, if you increase A0, there will be a stronger MOND effect, and you would expect to see discrepancy already in the so-called non-MOND regime flow. What you call non-MOND regime is for the A0, local A0, right?
Yes,
but if, let's say A0 is 4 times bigger than you are in the MOND regime, so you can test it.
Yeah, so it's this example, right? So here, for example, for this galaxy, A0 is almost a factor of 10 larger than it would be at...
maybe less than
27.
Right? Yeah, so actually, yes.
1 plus 2 to the cube.
27. 3 to the cube, yes.
No, not with these two galaxies, even with the higher redshift.
Yeah.
That would be even bigger.
In principle, you can.
No, I agree.
I agree.
And I think that for these two galaxies, we are indeed testing MOND right now because we have the HST photometry and the surface brightness profile, so we know the stellar mass distribution. In the other galaxy at high redshift, at the moment, we are putting in the bulge component by hand, right? So we can say it's consistent with what we expect, but the real test will be when we get the JWST images.
So Federico, you showed in the models of your rotation first probably those one that majority of them show the signature of bulges, right? So how is it consistent with the observation that the majority of local massive galaxies don't contain classical bulges?
Well, there are some local massive galaxies without bulges, but there are also many that do.
I think the statistics
including
is that the
Andromeda, for
majority
example.
are without classical bulges.
So
Maybe these are the pseudo bulges, or maybe we are looking at the progenitors not of spirals but of lenticular galaxies.
there is variety as there is at redshift 0. So look at this. Here you don't need a very big bulge. Maybe you can actually do even without any central component. There are others like this one where there's this inner decline that you really need a bulge. So it's a mixed bag, but I'm not surprised about it because galaxies are mixed bags to some extent.
Thank you, Federico. I was just wondering, in your initial slides, where you showed a ratio of velocity by dispersion, you got 22. Yeah, something on that. So this is at redshift 2.2. There was a paper in 2020 about a dynamically cold disk at 4.2, which had much less, like they had an upper limit of 9 or something like that. Is this as we go to higher and higher redshift? Are we to expect these values to go up, or what is your feeling about this?
So yeah, the general wisdom, let's say, is that the velocity dispersion increases with redshift. But I wouldn't, bet on it necessarily. And one has to be careful in comparing the same gas phases, right? Because, for example, we know at redshift 0, for example, the H alpha is typically higher velocity dispersion than the H1 and the CO. So when one compares different tracers, needs to be careful. In this specific example, I'm confident that the V over sigma ratios are high, then whether they are 17 or maybe 10, it's difficult work. But for sure there are disks that are rotationally supported up to high ratio. That I'm confident.
Question here.
First of all, great presentation. Very interesting work that you've done. I was wondering if you could comment on the conversion between the emissions that you've found to the mass. So for the 12CO, the 1 to 0 transition, it's like 5%, maybe 10 in terms of uncertainty. How big is the uncertainty that is relevant for the other transitions that you are using, like the 3 to 2 and the 4 to 3?
Yeah. So first we have to assume a typical line ratio to go, for example, from CO3 to 2 to CO1 to 0. And that can vary by a factor of 5, let's say, and we use some average value based on other observations, statistical value. And once you have an estimate of the CO1 to 0 luminosity, you have to assume a so-called alpha CO conversion factor that is well studied in the Milky Way. So for the moment, we use the Milky Way value. But actually, in the final numbers that I gave, we don't fit the gas mass. It uses a free parameter in fitting the dynamical model. And then we go check whether this gas mass is reasonable by comparing it with those numbers. And in general, we find for these two galaxies that, a Milky Way conversion factor and an average excitation ratio for the CO line is a good approximation. But, uncertainties can be a factor of 4 or 5 if you just take the luminosities.
So I think without further questions, we can move to the general discussions. Before that, let's send Federico.